All right, we're going to take a quick detour away from the angular momentum mind map because we need to deal with a question regarding a little more of the Dirac formalism. Because once we get into our study of spin and the poly two-component formalism, we have to blend this with the notion of a wave function. And in that blending, we go through this addition of angular momentum where you see we have these two operators being added together. And we really need to be careful because adding two operators together looks really simple in this context just by writing it down, but it's not. The simplicity belies an underlying structure to the formalism that you really have to walk through at least once to understand. In particular, the idea is that the L operator acts in a different vector space than the S operator. And so adding these two things together doesn't really make a lot of sense as it's literally presented here and typically presented in books. Now, many books do cover this notion of the tensor product space. Not all of them, but we are going to do it, and we're going to flush it out fully today. And then we're going to come back and finish up our story about the angular momentum mind maps, starting from the fundamental mathematics of rotations and going directly into the general angular momentum commutation relations, and never stopping through the classical beginnings of the subject like we did in the previous two. Okay, so today is about the tensor product space in the Dirac formalism.
So let's begin by talking about tensor product spaces in the Dirac formalism. To me, this subject is important because there's such a wide variety of different formalism out there. I should say they're all trying to be the same formalism, but the way the notation is done is so different that it is just magnificently confusing. And but it is I love reconciling formalism. I think I really enjoy that part of studying physics. It's like the least interesting thing out there, but in some sense, it also is very edifying to get to the bottom of things. So let's start from the bottom up here. Meaning we are going to presume that we have a vector space V, and it is n-dimensional, right? It has n dimensions, and it has a basis, which we'll call En, right? Those are the basis vectors. I won't put I'm tempted to put an arrow on top, but it's just a thing. Just when you see E sub n, that is a basis vector in the vector space V. And any vector in the vector space V can be represented by a sum over n, where we use the Einstein sum convention, right? So we're kind of back to this notation of just talking about general n-dimensional vector spaces. Now, we know that when we have the n-dimensional vector space, we immediately pop into existence the dual space. And the dual space has basically the same properties, same dimensions. It has a collection of dual vectors, which we will call En, right? So En is just a vector in the dual space, and the distinction between the vector space basis vectors and the dual space basis vectors is this raised index. Actually, n is not a good choice because n is the total number of dimensions, right? So let me change that. Okay, so we're going to use little index I here. And the link between these two, right? Remember the whole story about the one-to-one correspondence, that link between these two? We're assuming that link exists, right? There's this inner product over here on the vector space that we will call the inner product on vector space V. And so that creates this link between vectors and dual vectors. So when we study general relativity in the general relativity section in the what is a tensor series, actually, this is exactly what we did. That's just the same notation and everything we did before. But we know we have a space and we know we have its dual space. Now, in our quantum mechanical notation, everything in the vector space was given as a ket. So a general vector would be given as a ket, and its associated bra was given as a bra. And it was a complex vector space. So we'll assume these are complex vector spaces. So now we have two different ways of expressing a vector. We have this sort of vector notation, or this what we call covector notation because it's in the dual space. But remember, the dual space is just a vector space. It's just a vector space where these objects are maps that take vectors into the complex numbers, the field of scalars. So we turned this into, using the Dirac notation, we turned this very basic mathematical naked vector space into this ket space and into this bra space. And then, of course, the inner product was now expressed as A, right? Which really was the ket A inner product with itself, right? That's utilizing this inner product that's defined on the vector space, right? So now we write it this way, and that's because we've linked these two together with a one-to-one mapping driven by this inner product. In other words, we define the bra such that this mapping acting on its dual in the vector space was always guaranteed to mimic the inner product that existed on the vector space. Okay, a quick review of that. So the next thing we learned, though, was that we could create tensor product spaces. We could create objects called tensor product spaces. Once we had these two things, we could create tensor product spaces. And the way we defined a tensor product space is we wrote, for example, V tensor product V. And this guy here is a new vector space, meaning that it has its own dimensionality, which happens to be V squared, or the dimensionality of V squared, and it has a basis. And the basis vectors are written as E sub I, little tensor product, E sub j, where I and j run over all of the run over the entire dimensionality, so from 0 to n minus 1 or 1 to n, depending on how you want to count. And these guys here are basis vectors. They're not to be understood. You never think of this in terms of EI tensor product EJ equals something, right? If you did put something over here, it would just be a renaming of what this is. This is meant to just look, this is meant to be a basis vector. And so you have the basis vector E0 tensor E0. You have the basis vector E0 tensor E1, etc., all the way to E, I guess the way I'm counting, n minus 1 tensor E n minus 1, right? And every combination is represented in the basis. So that's why you have n squared bases. N squared dimensions, you have to have n squared basis vectors. And we would write in the old system, the arbitrary element of such a thing would be the vector B, I guess I will put a little vector sign over there, is given as B I J E I tensor product EJ, where this is just understood as a basis vector. You could rename the basis vector in a different way if you really wanted to. You could write Bij and you could write Eij. And now this guy represents all the possible basis vectors. But you know, it's nice to keep it with this little tensor product symbol in there, just so you know that you're dealing with a tensor product space. I mean, if seeing two indices should be good enough, but it's nice to have it there, I think. So we leave it that way. The point is this notation looks, when people see it, they get kind of intimidated because it looks like some weird abstract math. But it's just, that is nothing more than a basis vector for a new vector space, which is called a tensor product space, which is just V tensor product V. But then what we learned is that you could have done this with V tensor product V dual, right? You could have written that thing out, right? Or you could have written V dual tensor product V, right? Or you could have written V dual V dual. All of those are legitimate tensor product spaces. And the differences then are basis vectors. For example, in this particular instance with V dual dot V dual, these I's and J's would now have to go in the upper position, right? Because they reflect the dual basis vectors, right? So this now becomes your basis. And this goes from your arbitrary vector goes from this notation to I, J, E, I, E, J, right? So that's how this tensor product space would look. So obviously we've immediately found 4 new tensor product spaces, right? But that is not even where it stops, right? Because we could, of course, we could have, and we did in the tensor relativity section, I could do another tensor product space, right? And then in that case, the basis vectors would be EI, tensor EJ, tensor EK. Now notice how this is an overloaded operator, meaning it's being used for different things, and the way it's being used is interpreted by what kind of object it's between. V is an entire vector space. So this tensor product takes 2 vector spaces and makes a third vector space, and then this tensor product taking that vector space and creating a tensor product with this vector space. So this is the tensor product of vector spaces. So this is a way to create new vector spaces from old vector spaces. Down here, the same symbol is being used between literal vectors, right? This guy isn't understood to be an element of the first vector space. This guy is understood to be an element of the second vector space. Likewise, an element of the third vector space. So this represents a new vector being created from old vectors. And this new vector is an element of this tensor product space, right? This vector here is an element of that tensor product space. This vector here, because this whole thing is associative, and it's associative in a sense, right? Meaning that this vector is this guy tensor product here, but it's also this guy tensor product into those guys. But anyway, this vector is an element of this triplet, sort of triple vector, or rank 3. This would be called a rank 3 vector space. Specifically, I think it's a rank 3, 0, right? The way we talked about it. Because this is the number of dual spaces, and this is the number of vector spaces. So this is a rank 3, 0 vector product space. And notice what I called it. I called it a vector product space. See, so the formal meaning is the tensor product space. Often this is just called a vector product space. So we got to be careful. The use of the word vector in this case is really used all over the place for different things. First of all, it often means a literal vector in 3-dimensional space, right? And we will use it that way, right? We will use it that way in a moment because we're interested in 3-dimensional rotation. But what a vector is a vector is an element of a vector space. That could be V, could be V star, could be this tensor product space. So an element of any vector space is called a vector, but an element of certain vector spaces have its own name, right? Like an element of V would be called a vector. An element of the dual of V is sometimes, frequently, if not most of the time, called a covector. Likewise, an element of a tensor product space is a vector because a tensor product space is a vector space. However, we tend to call these guys tensors, right? If you live in a vector product space. In quantum mechanics, they very, very, really rarely use the word tensor, right? They will call elements of a vector product space is just a vector in the product space of vectors. So, so we have to get used to that because that's different than in general relativity. Okay, so now the question is what does this look like in the Dirac formalism?
Oh, oops! Before we move on to the Dirac version of this, there is a new twist that also appears in quantum mechanics that's really important that does not show up in general relativity much. Notice that our tensor product spaces, the way we've been talking about them here, right? There's 2 issues. First of all, it's all built off of the initial vector space V, right? Everything is V or V dual, but that does not have to be the case. We could have had a vector space V and another vector space W, totally unrelated. Matter of fact, D could have dimensionality 2 and W could have dimensionality 20, or even infinite. And we can still create V tensor product W. If V has the basis vectors EI and W has the basis vectors FJ, the basis vectors of this would be, E sub I tensor product F sub J. And this is still a tensor product space, but the underlying vector spaces are totally different. And that's fine, because all we're looking for is the new basis vectors, and you could still be a vector that lives in this thing, and you would still have two indices. You would still be Aij, EI, tensor product Fj. It's just the J might have 20 possible values, and I might have 2 or 4. Or J could be a countably infinite number of possible things. In quantum mechanics, the vector spaces we assemble are always like this. In general relativity, when we build up the theory, you're really dealing with just V, which is the same dimensionality as space-time, which is 4 dimensions. So you don't see this very much in general relativity. But you do see this all the time in quantum mechanics. So there is this technical notion of how the literal word tensor is defined, right? And we're not going to play around with that. Anything constructed in this way, we're going to call a tensor, right? There is this technical question of a true pure tensor has all the V's in front of all of the V stars and doesn't have any W's in it, right? In other words, this guy, there's a technical definition of the word tensor which wouldn't include this, but I mentioned that a little bit in the What is a Tensor series, and it caused some confusion, although it is correct. But the general language is this is a tensor product space of its constituent vector space V and W. And also notice that V tensor product or W tensor product V, these are not the same, right? These are not the same tensor product spaces. Order matters. Order matters. Because the basis vectors for this guy is Fj tensor product EI, right? And its components would be AJI, right? It's very similar, but it's not the same. It's not the same, technically speaking. So the point is we're now going to discuss the Dirac version of this, and you're going to see that we're actually going to build these tensor product spaces from different vector spaces. Okay, so now let's study the Dirac formalism version of all this stuff.
All right, so in the Dirac formalism, we are going to parallel everything we just did. So let us consider one quantum mechanical system, and the kets of that quantum mechanical system are labeled, I'm going to draw a typical ket with the letter alpha. Well, what do we know about alpha? Well, alpha is a member of a ket space, which is a vector space. So we'll call that vector space V. We've been using V for the vector space. So the kets are alpha, and V will have some basis of states. For example, let's say it was a free, some kind of particle, and that particle had angular momentum and position. No. Let's just use energy eigenstates, right? So V is a particle. There's some Hamiltonian operator H hat that has its set of states N, right? So the eigenstates are going to be N. So N is now our, by the virtue of quantum mechanical postulates, N is now our complete set of states which become the basis for the vector space V. All right, so we've got those states. So I need to sort of look at this ket. Now I know I'm saying ket lives in this vector space which we call V. Well, what am I going to do to identify that A lives in V? Well, I'll probably put a little V here just to signify it. I could do a color. I could put all the kets in green. Well, let's try that. There. So now V is the blue vector space, right? So now I can imagine a different vector space. And that vector space is going to be, let's say, W. Now this second vector space is associated with a different particle, right? We could literally call this guy particle 1, and we could call this guy particle 2. And the Hamiltonian for particle 1 is given by H, and the Hamiltonian for particle 2 is given by Q. Q has a basis set of vectors that we'll label with M, and those are the eigenstates of the Hamiltonian for particle 2, and likewise over here for particle 1. So these are two particles that are described quantum mechanically, and what's important to understand, of course, is that something that makes no sense is H on M. Well, now I'm using colors, I got to stick with it. Right? H acting on M, this Hamiltonian acting on this particle, it makes no sense. And the reason it makes no sense is that H, this is a linear operator, and a linear operator is something that acts on a vector space, right? But it acts on a specific vector space. This is a linear operator designed to act on the vector space V. It's not a linear operator designed to act on the vector space W. So this is nonsense. It makes no sense at all. If you want the Hamiltonian to act on M, you've got to use a linear operator that is designed for this vector space. Now something we need to notice about linear operators, right, is if I have two linear operators in the vector space V, say H and say K, right? What do I mean by H plus K, right? What do I mean by that? H plus K is two operators. Well, operators, what do? They operate on vectors. So whatever I mean by H plus K, it should be able to operate on some vector from the blue vector space alpha, from the particle 1 vector space. But of course, everything's linear in this game. So what I mean by this, of course, is H acting on alpha plus K acting on alpha. And this guy is going to return some new vector, right, which we could call, well, what we might call it is we might call it the vector H alpha, and we might call this the vector K alpha. But keeping in mind that this is sort of an abusive notation, right, because H doesn't act on a name, right? Alpha is the name of this ket, and here we have H acting on the name put into a ket, but H has to act on a vector. So this is sort of an abusive notation to do it. That's what they typically call it in books. And like I said, computer scientists have sort of figured out what this means. This is a new label, right? HA is to be understood as a label. And you'll frequently see this, Griffiths makes a big deal about this, use of notation. And the reason you want to abuse notation, I mean, people abuse notation because it's convenient, because otherwise I'd have to write beta plus gamma. And now I have to kind of keep track, where did beta and gamma come from? And you've got to sort of wind your way back to, oh, the beta is the vector returned by the operation of the linear operator K on the state alpha. Right? Well, it's much easier just to write, okay, K alpha. So I know exactly where this ket came from. And I think in my mind that this ket is defined to be K acting on the ket alpha, right? Okay, enough of that. The point is that it's very easy to understand the sum of two linear operators. It's defined in this way. Likewise, I can take an operator H and I can multiply by a complex number, and that creates a new operator, and that new operator acts on alpha as the complex number times the operator acting on alpha. It's completely linear in this regard. So you can multiply any operator by a scalar quantity, and you still have an operator. You can add two operators together, and you still have an operator. And you can take H, and you can add to it -1 times H, and you can get the zero linear operator, right? And zero linear operator is a linear operator, where 0 acting on A is 0. And every vector space has 0 in it, right? So this is an element of the vector space. So the point is that linear operators themselves form a vector space, right? And that's very important for our understanding of how we build tensor product spaces in quantum mechanics. But it is important to understand linear operators form a vector space. So I can actually now associate with V and with W another space, a space of the linear operators that act on V, and then a space of the linear operators that act on W. So let's do that. So now I have these sort of four vector spaces floating around: particle 1's state space and the operators that act on particle 1, and particle 2 state space and all the operators acting on particle 2. So now what do I want to do? I want to form the tensor product space between particle 1 and particle 2. And formally, that's going to look like this. It's going to look like V, I guess, tensor product W. I'm kind of going long on the colors here. I'm giving that a try. But V tensor product W is completely legitimate state space, and it has a basis. And a typical basis vector is N tensor product, is N tensor product M. So for example, I might have the ground state energy tensor product with the ground state energy. And this is a basis vector, one of the basis vectors of this tensor product vector space. And likewise, I might have the first excited state of particle 1 and the ground state of particle 2. You can almost imagine like particle 1, it's some unspecified Hamiltonian. This might be a harmonic oscillator, and particle 2 might be in its own harmonic oscillator, right? That would be a good way of looking at it, or a particle in an infinite square well, or for that matter, a finite square well. But this now represents a basis state of this tensor product space, which is essentially combining these two systems into a single system. So if I take two independent systems and blur them together, and I want to create one system out of it, what I'm really doing is I'm creating a tensor product space of the two. And the new basis system for that tensor product space is something that looks like this.
Let me clean this up a bit, because I just realized we need to sort of change the definition of the Hamiltonian if we're going to go with this harmonic oscillator analogy, because before I'd written this down, and it implies that we're labeling the states with its eigenvalue. And then I kind of said, oh, well, we're going to use the ground state, and I labeled the ground state 0, which means you'd pull out a 0, right? And you would get h of 0 equals 0, which equals 0. And that, of course, is not what I want. I do want 0 to represent the ground state, but I don't want the ground state to literally be the 0 state. So in conjunction, in keeping with the harmonic oscillator, the eigenvalue that these guys are going to pull out will have some finite piece here. So when m is 0, you still get something out of it. I think typically in the harmonic oscillator, it's a half, right? But actually, maybe I'll just make it 1, because I don't want to confuse anything further. Okay, so this is the relationship. It doesn't change the fact m, the core of our notation, in the sense that they will represent the complete set of states. And by the way, I could have used n here since I'm going with colors. I've kind of double changed things. So, but the point is we still have these two vector spaces, and their tensor product space is still represented in this way, where we have all of the possible basis vectors. Now I'm a little comfortable with 0 being the ground state, because I've eliminated that possibility of Q acting on the ground state, giving you the 0 vector. Okay. And then there's the two operator spaces. And these two operator spaces are their own vector spaces in their own vector spaces, but these guys all operate on V, these guys all operate on W. So of course, now we need operators that act on V tensor product W, and it probably shouldn't be a surprise that the operators that act on this tensor product space are going to be the tensor product space of these two operators. So now we need to create that space. And there we have it. This is done. So now we take, this is set all the basis operators. I mean, these are vector spaces. I mean, so you can create basis operators that all operators can be constructed from. And you can create a tensor product space of operators. You don't usually do that. You don't usually worry about the basis of this space, but we do have to understand that you can create the tensor product space of two operators. And the reason is ultimately when we write down J equals, when we write down that the total angular momentum equals the orbital plus the spin angular momentum, we're actually going to understand this in terms of this tensor product space. It's not obvious how that'll happen now, because right now we're talking about two different particles altogether, completely two different particles. But this is a very, very important element to understand how all of this stuff works. So our next step is to develop a shorthand. We're now going to create a shorthand notation for these basis vectors. Instead of writing 0 tensor product 0, we're just going to go 0, 0. And instead of writing 1 tensor product 0, we're just going to write 1, 0. We're going to squeeze them all into a single ket, right? And these kets are now going to be the kets that live in this vector product space. I'm using the word vector product space now because that's the way we use it in quantum mechanics, but it is a tensor product space. But these kets that have two labels live in this vector product space. And they're just defined this way. So these equal signs really should just be triples, meaning it's just a definition, right? There's no material difference between this and this, except that this is a little easier to write. So these are legitimate kets. These kets have two labels. And you should start thinking, when you see kets that have multiple labels, you're actually dealing usually, with a tensor product space. And that's what we have here. We have these kets with two labels that live in this tensor product space. And so now we would ask the question, all right, so what about H, right, the operator that acts on the V vector space, right, the vector space of particle 1. I'll put my particle names back there. The vector space that acts on particle 1. And so if I want to take that Hamiltonian operator and I want to operate on the state 3, 2, right? That's one of these, right? There's all possible basis vectors are here, so there's one of them, and it's in shorthand for 3, 2, right? Well, does that make any sense? Can I write this down? And the answer is no. No, because H operates on the vector space V. H does not operate on the vector product space VW. So this makes no sense. You can't write that down. What we can write down is we can write down an element from here that does the same thing. We can write down H, tensor product, the identity operator, right? Because the identity operator will always live in P. And that operator acting on 3, 2 will give us, 3 plus 1 times 3, 2, right? And the way we understand this is literally what's happening is I fixed my color. So is H tensor product 1, an element from this, acting on 3 tensor product 2, which is an element from this, written in longhand as opposed to shorthand, and H acts on the 3, and the identity acts on the 2, and we ultimately will get 3 plus 1, 3 tensor product 2, because the identity operating on 2. And then this gets converted to shorthand 3, 2 again, and you end up back up there. And of course, it's always linear in the numbers, in the scalars. So we have to understand this is what's going on. Usually when you have multiple quantum numbers involved in systems, is you can usually find a tensor product space that's really more relevant to describe the system. Not always, but usually. And certainly when you have two particles, that's what's going on. So the reason, so the point is that this is all thrown under the hood, though, right? You're not allowed to write you're not allowed to write this, but we do it anyway. We do it anyway. And all that stuff we just talked about, this being actually a member of this tensor product space, H operating only on this vector space for particle 1, we kind of throw that under the hood and we assume that you understand that no, this H is now being sort of converted into this kind of construction. So it is now allowed to operate on a member of the underlying tensor product space, and it gives you this result. And so all of this mechanics sort of goes on in the background when we write these, I'll say ruly, like ad hoc rules, or sort of, I guess ad hoc is a good word. It's sort of, we invent this rule and we don't really realize, we're talking about linear operators in different spaces. So you have to create these new tensor product spaces. And this is all pretty easy to do. In some sense, these operators, these two particles are totally independent, right? We're just creating a system that encompasses two different particles in this case. But you can easily imagine that you can now create operators in this space that do things to both particles, right? You can imagine, for example, that, let's create a little bit of an example like that. All right, for this example, we're going to go to the notation where we use subscripts and superscripts to make distinctions between everything, because textbooks don't use colors, so that other notation is kind of fun, but this notation is a little more standard in textbooks. So we're going to talk about two particles again, the V particle and the W particle, not to be confused with the W boson. These are just two names. We're going to presume they're sort of electrons or something. And we're going to talk about their orbital angular momentum. Their orbital angular momentum, the sort of the classical analog angular momentum. And the V particle will be in the state where the total angular momentum is given by the quantum number 1. So its eigenvalue would be 1 times 1 plus 1, which would equal 2, okay? And the W particle will be with a quantum orbital angular momentum of 2. So those are fixed numbers, which leaves us with just one quantum number left, which is m. And in this case, m can go from +1 to -1, and here m can go from +2 to -2. So this is a 5-dimensional vector space, right, with all the different values of m, and this is a 3-dimensional vector space, all right? So now I've taken that harmonic oscillator idea of where we have infinite dimensional vector spaces, and now we're just looking at two finite dimensional vector spaces. And we can create the tensor product space of these two particles. You have to presume they're in some kind of condition that's not going to change their total angular momentum, right? It's a angular momentum, total angular momentum is conserved system altogether, but the projection might change for whatever reason. Or a particle, they could have any value of this projection, angular momentum. So the tensor product space would literally be written where you take a basis vector. The basis of the tensor product space would look like this. You have to choose m from the V particle and m for the W particle. And you could write it out in full glory with the tensor product symbol, or you can write it in this compact form where you have the 1, the 2 are sort of established in there, and you know that the first two labels represent the V space and the second two labels represent the W space. But you could, once you do this, you could shift those labels around and you could write, no, I want to know the total number angular momentum for V, the total angular momentum for W, and then the projection for V, and then the projection for W, right? So, you could define the order of these things to be any way you want. The point is, it doesn't matter how you define these labels, you're still talking about this tensor product, all right? And then the operators, if I want to know the total angular momentum of the V operator, of the V particle, I have to create this operator and operate on this tensor product, like so. And what I should end up with is mv times, and it's an eigenket, right? So I should get back the same state, right? So I should get back this thing again, right? Just like this. But notice that the whole point of this is to show you that the operator that we're actually using is this thing, this tensor product operator. It's not just LV squared acting on this, right? Now, the reason I'm pointing that out over and over again is, like I said previously, we sometimes write it this way anyway, right? And when we do, it's fine. You just have to understand that this guy is actually a member of this tensor product space, and this guy is actually this thing right here. Likewise, if I wanted to do this for the total angular momentum of the second particle, I would have to use this operator. And I would pull out, in this case, I would pull out, whoops, wait, why did I pull out MV? I shouldn't have pulled out an MV. I should have pulled out, because this is the, remember, this is the total angular momentum. So I should have pulled out a 2, right? 1 times 1 plus 1. And likewise, this guy here would pull out a, this guy would pull out a 2 times 2 plus 1, which is 6, right? Right, so this would be this result here, right? But again, it's all sort of shorthand, right? Well, this is the longhand way of doing it. But what's important is that what if I wanted this kind of thing? LZ plus LZ for W, for V and W. What I mean by this is actually this, right? Because you can't add an operator that operates on the V vector space to an operator that acts on the W vector space. This, and the reason is because the vector space of operators that acts on V is different from the vector space of operators that act on W, and there's no such thing as addition between vectors from two different vector spaces. So this kind of is nonsense. But what we understand it to mean is this, because this is a vector that lives in the operator space of V tensor product W, and this is a vector that lives in the operator space of the operator space of the vector space V tensor product W. So these two vectors live in the same vector space, so addition is very well defined. And we can execute this, and we would execute this, it would look similar to what we did up here, but now you sum that and that together. And I guess you're pulling out M instead. So, okay, so what would it literally look like? And it would literally look like this. This guy operating on this ket would give us MV times the ket. This guy operating on this ket gives you MW times the ket. And that's just MV plus MW, which is kind of what we wanted, right? That's what we want this to mean. Now, we typically do write this down this way, but you have to understand that it means this. It means this. And I can't tell you, understanding how this worked, really, my quantum mechanics really increased rapidly once I started peeling apart how these tensor product spaces worked, because otherwise everything looks like a bunch of crazy ad hoc notation. It's not hard to learn, and yeah, I got through all my exams, but there was sort of this idea that when was the next ad hoc curveball going to come my way? So having a formal understanding of how this works is really good. And by the way, the next step of the formal understanding, of course, is to shrink this down into the ad hoc-ish single ket that lives in this vector space, like, for example, this ket right here. Right? So even this is more formal than what you normally see in quantum mechanics, which would be this thing right here. Okay, so where are we? Well, we studied today, we focused on tensor product spaces in the Dirac Formalism. We began with the story of tensor product spaces just in general with vector spaces. And we emphasized that in quantum mechanics, when we form these tensor products, we're usually doing it with totally different vector spaces as opposed to a vector space and its dual space, which is how we did it in the What is a Tensor series of these lectures and in our study of general relativity. So if you're coming here from those lessons, this is a fundamentally different idea. If you're starting here fresh, then the tensor product space of two different vector spaces is all you need. It's an operation on two different vector spaces that returns a third vector space. And we talked about how to create a basis for such a thing. And then we converted this immediately into our Dirac Formalism, where I think the one I used was this, where we created the tensor product space of two state vector spaces, right? This is a state space for the W states, the V space state space for particle 1, and the W state space for particle 2. Actually, I have too many names for things, right? This is the particle 1 state space. This is the particle 2 state space. And then the tensor product space is now a unified space that takes both particles into account. When you do the Einstein-Podolsky-Rosen stuff, you're dealing with two particles, right? So you immediately create this state space of tensor product space between the two, right? You say, particle 1 is spin up, particle 2 is spin down. Well, that's actually the tensor product of particle 1 spin up, particle 2 spin down, written in shorthand, right? Now, we don't have the spin stuff down yet, but that's coming up next when we do the Pauli spin formalism. So then we talked about how the operators in this tensor product space are really written as tensor products themselves, because an operator can only be defined to operate on an underlying vector space. And an operator designed for one vector space cannot operate on another. So if you create a tensor product space, that's a totally different vector space from either particle 1's state space or particle 2's state space. It's a state space of particle 1 and particle 2. So it needs its own set of operators, and those set of operators are defined to be living on the tensor product space of the operators. And so that's when we introduced this idea, and then we expanded on that here, right, where we took our two particles. I kind of shrunk it down to finite dimensional vector spaces to show you how that might work. Right, if we just left this with L instead of 1 and 2, we just left that with L sub V and L sub W, then they would be infinite again, because there's no limit on the angular momentum of a particle. And then we kind of just showed how some operators would work on the various, through the formalism, right, through the formalism. And we made sure that we understood the shorthand notation for things. So you can fully expect to see stuff in quantum mechanics books that look like LV acting on 1 MV 2 MW. You can see that all the time, and you have to, in your own mind, say, well, wait a minute, what he really means is L, Z, V, tensor product, the identity, and what he really means by this is 1 MV tensor product 2 MW, right? And eventually, if you make that replacement a few times, and eventually you don't have to worry about it, you can live with the sort of abused notation version of everything. All right, so now that we understand these tensor product spaces, we can now study the Pauli spin formalism, which will allow us to instead of merge the state space of two particles, what we're doing is we're taking one particle that has two different characters that are quite distinct and can be described as two different vector spaces. And the one particle will be described as the tensor product of these two different state spaces. For example, the wave function of its spin, the wave function of an electron's position, its position wave function, and then it'll have a part that will reflect its spin. And the spin will be a two-dimensional vector space, and the position, of course, will be a continuous infinite dimensional vector space. And we're going to combine them together using the tensor product formalism. So we first have to create this two-dimensional vector space representing spin, and we'll do that in the next lesson.